In this video today, we'll be talking about Ohm's law and some circuit analysis. Ohm's law states that the voltage across the conductor is directly proportional to the current flowing through it. What this means mathematically is that we arrive at the equation V equals I times R. This may look familiar in the previous video on resistance. As we know, to find resistance we use the formula R equals V over I. But for those who don't know, V equals voltage, I equals current, and R equals resistance. An easy way to memorize this is to draw out our triangle. So that's how you get resistance. You get V over I to get voltage, get I times R, and to get current, you get V over R. Let's do a quick example to solidify our knowledge. So I've drawn out this simple circuit here where we have a 6-volt battery hooked up through a resistor of 1000 ohms. We want to find the current. So using our newly taught Ohm's law equation, I've drawn out our triangle here already. We can find the current. So the current will equal I equals V over R. We have our voltage, we have our resistance. So we substitute the numbers in. 1K, that's 1000 ohms. We will arrive at, so if we put that into our calculator, 0.06 amps or 6 milliamps. Easy. Now, what we have done, as you can see, is that we have used this law to calculate required values to know what values are going through our circuit. So we can use this for even more advanced circuits later on. Let's take a look at some series and parallel circuits first. So I have this circuit out here, and we want to find the total resistance of this circuit. Now this is a combination of series and parallel. This is our series, this is our parallel. We want to find the total resistance. How do we do this? Well, we're going to need to split it up. And if you remember, resistors that are put in parallel, we can find them by 1 over R1 plus 1 over R2 plus, how many more. But the nice little trick here, if we only have 2 resistors in parallel, we can find it faster by using this. So R parallel equals, so if this will only work if we have 2, R1 times R2 over R1 plus R2. Well, this is a nice way to find out our parallel resistance if we have 2. So let's solve this. How do we find the total? So we got a series here, so equal to R1. That's our series. I want to combine this, so we'll need to find the total of these 2 resistors first before anything. Put the brackets there, and R2 parallel with R3. That will give us R1 plus, since we have 2 parallel resistors, can use that. Just move that up a bit. So now that we have that, let's solve this first. Let's solve our parallel first, I'll just do it on the side here. Just name it RP, or parallel. So I substitute our numbers. So our R2, I see I've made a little mistake here. That's supposed to be R2, R3, 2, R3. Very sorry about that. May have caused some confusion. So let's solve this. So R2 is 2000 ohms. R3 is 2000 ohms. And we just substitute them here. Now you may have noticed I've only put 2 and not 2000. As long as we're working in the same form of units, we can just add on the K at the end for the 1000. So this will equal to 4 over 4, which equals to 1. So that'll be 1 kilo. That is the parallel resistance. And what you'll find is that now that we have this, we can now redraw. Yes, I'm being quite tight with space here. This is now our new circuit, because we've combined those two resistors. So I can see here, this is now just a series circuit. So what we do with series, just add them together. So the R total equals to R1 plus RP. Substitute our numbers, we get 2000 ohms. So moving on to a bit more advanced circuit here, I'm going to find a few values that we need to calculate. As I mentioned before, with Ohm's law, we can use that law to find current, voltage, resistance of our circuits, and very useful law. So I'm just going to show you how to do just that to show its effectiveness. So we're going to have to find, first off, we want to find the total resistance. Now, as you have already started the equations. I'm not going to write out, it's just the same thing as we done in the last example. I'm not going to write out the total equation as I've just shown it. So I'm just going to substitute straight our numbers. So our 220 ohm, 1000 ohm, 2200 ohm, resistors all substituted in. You want to solve that, we'll get 220 plus 688 ohms, and that equals 908 ohms. Nice. So why did we solve this? Why did we find this? So maybe we want to find the current supplied by our power source. In this case, it's our 6-volt battery. So I'm going to use Ohm's law for this. Draw a triangle. So this will equal to, to find current, we had voltage over resistance. Substitute our values. 6 over 908. We get 6.6 milliamps. So now we find the current supplied, by our power source, in this case the battery. Now we want to find the voltage drop across each resistor, and you'll find that when you use electronic components, you need to, well, when you make your circuits, I should say, rather, yeah, well, anyway you go, I mean, is that you'll find there are voltage drops across each component, and you need to compensate for that. So just be wary, and we're going to do that to find the voltage drop across our resistors here. So using Ohm's law again, we can, using Ohm's law, V equals I times R for our series resistor. So that equals 6.6 times 10 to the power negative 3, because milliamps, we need to convert it to amps, times 220. That gives us 1.45 volts. So this is 1.45 volts across this resistor right here. Now we're gonna find the power resistor. So to do this, to get our, let's call this V1, to get our V2, get our supply, minus V1. Now supply is 6 volts here, so we do that, we'll find the remaining voltage that's coming across these resistors. Now, I should mention that in parallel circuits, the voltage is the same, regardless. In series circuits, the voltage would be different. So the voltage from here to here is the same. So we substitute our values, 1.45, and we get 4.55 volts. Nice. Now we want to find the current flowing through each of these resistors. So to do this, we will apply Ohm's law again. Apply Ohm's law again. Just apply Ohm's law. Current equals voltage over resistance. We're doing this for 1K. That gives us 4.6 milliamps. Voltage is the same in parallel circuits. So I2 equals 4.55. This is our remaining voltage from here, so you don't get lost. Then we get 2 milliamps. Nice. So if we just draw this out, there is 6.6 milliamps flowing through here. There is 4.6 milliamps flowing through here. And there is 2 milliamps flowing through here. And if you notice, when we add these back together, they become back to 6.6 milliamps. This is a good way to check that if our calculation is correct. So we see we got it correct. Calculations are all good. So just a small part before we end off this video. I think it's a bit of a longer one, this one. Talking about power, this ties in nicely to Ohm's law. You may have gone out to buy resistors or other components now. Notice they have a rating with the letter W. So you might see this, for example, on a resistor. And that means that is power. That is power. And the unit for power is watts. So watts, and SI unit is W. The formula for power, P equals VI, which we know, voltage and current. And the thing about Ohm's law that I want to tie in so nicely is that we can use Ohm's law to make this equation more convenient for maybe things we do not have, for values we do not have. So for example, maybe we don't have our voltage, and we know from Ohm's law that voltage equals I times R. we substitute that in. I times R, I, we get I squared R. We get I squared R there. And for example, we get for our current, so our current there, where we don't have current, we can use Ohm's law, voltage over resistance, so that equals V over R. And that would give us V squared over R. Of course, we'll go in more into power in a later video, but I just wanted to tie this in nicely because I thought it did. And in the next few videos, we'll be talking a bit more about power, and I'll explain further. So that's all. Thank you for watching, and next time I think we'll be talking about capacitors. Be a bit longer, but we'll see.